cell is Nij. In other words, they don't all have to be the same. We can have differing sample sizes in the cells. So that's what we mean by saying unbalanced. So what happens when the data is like this? We have unbalanced data in this two-factor kind of layout. Well, here's some things that we do. First of all, we can get the cell means. So here's a table of cell means. Notice the dot notation being used there to express what's going on. I see a typo there, that 3 should be a 2. Right? Second row, column B. The rest looks okay, I guess. Then the totals, and then these bars are wrong. So scratch those bars out. They belong over here, means. And going down the columns, that looks okay. The column means, that looks okay. Notice again the dot notation being used there. And then we have an overall total and an overall mean, just put down there in the corner to put in someplace. I knew I could do that. Sorry, remind me to do that every time. I forget. Whoops. Remind me not to go that far. So notation similar to what we used before. We have the total in the IJ cell, the mean in the IJ cell, the variance in the IJ cell. Now, in I dot is the row I sample size. So in the ith row, I count how many observations are in that row. That's Ni dot. And then doing the same thing down the columns, we get N dot J. Adding up how many observations are in the various columns, we get N dot J's. So these are different in an unbalanced case, and so that's where our problem begins here. The total sample size is capital N, little n dot dot would be the right notation for it. So there's the layout of our stuff to get started on this problem. So we have a model equation. We have a mean for the IJ cell. We call that the cell means model. And then we can also alternately write the model in terms of these effects, alpha, beta, alpha, beta. This is called the effects model. So we can write the model in either of these two ways. In the effects model, there are some side conditions that must be met. So here's a side condition on the alpha I parameters. Notice the sample size comes up in this side condition here. And there's a similar kind of side condition about the beta J's. Notice how the sample sizes come up in that side condition. And then there's a similar side condition about the alpha beta, some there and there. So guess in my view, I would just say this is a little bit awkward. Usually when we write down a statistical model, it just sits there as some kind of static entity describing the state of the world. And it's got nothing to do with the size of any data set that we might have about it. This is different. The parameters in the effects model are dependent on the sizes of the sample. That's what I'm saying, to me, is an awkwardness. But there's some reasons for these side conditions that we're not going to need to get into, but so let's just leave them there as the standard side conditions for this problem. So then we turn to sums of squares. We have a sum of squares total. If you look at this formula, you'll notice it's the same one that we had before. No change. Look at the sum of squares cells, as I've called it here. I think in earlier handouts this might have been called sum of squares treatment even. But let's just leave it be called sum of squares cells. And here's the formula for it. And if you look at this, this is the same as our formula from before. No change. Then there's a sum of squares error. There's the formula. If you inspect this, you'll realize this is the same formula that we've encountered before, and it's also expressible alternately in terms of the Sij squares, the variances in the individual cells. So anyway, these three sums of squares are old, familiar creatures for us, and we have this kind of breakdown here. The sum of squares total is the sum of squares cells plus sum of squares error, and the appropriate degrees of freedom are underneath here, which we've encountered before. So now we do like we did before. Let's take the sum of squares cells and try to break it up into pieces. So we define a sum of squares A this way, and that's a familiar formula from before, although one thing that's different in here is we have ni dot instead of n. Actually, I think we had, because this is for A, that's the row variable. We're summing on I this way. I think before we had something like NB. Now, the NB was the number of observations in a given row. So in this case, ni dot. So notice the change there. The rest of this is all the same. And so we do the same thing with B, defining sum of squares in that way. So these are natural ways to define these sums of squares. From what we had defined before. And then lastly, the sum of squares interaction AB is defined this way. And notice it has sample sizes Nij in there, whereas before that would have been just N, since it was the same in every cell. So we have that modification. The rest of the pieces are the same. And in all of these cases, the last formula on the right is what I call a hand calculation formula. If you're doing it by hand, those formulas are easier to use than the first formulas. This is a simple breakdown. Mean in the Ij cell to the overall mean is this difference plus this difference plus this messy thing here. And if your eye scans across this stuff on the right, you can see that there's cancellation there to leave me with what's on the left. Now here's where the trouble comes in. emphasis, notice that sign says not equal. Okay. Oops, I think I'm hitting this button. So what we did in the balanced case was the sum of squared cells was decomposed into three components, A, B, and AB. That doesn't work in this unbalanced case. So we have no equality there. The sums of squares have appropriate degrees of freedom, which are indicated there. And so I've listed two ANOVA tables. This first one is fine. We have sum of squared cell there in that one. But this one, and I emphasize this table is false, not valid. So what's false about it is that the sum of these top ones isn't the bottom one. Something is amiss. The degrees of freedom are added in nicely, so there's no problem there. But then when we form mean squares and then F ratios from these mean squares, these are just no good. So there's a temptation to think about how did we do things in a balanced case and try to do the same thing in an unbalanced problem like this. And the point is it doesn't work. So somehow put a big X through those. Those are not possible F tests. So what can we do? So here we go back to the cell means model, which is the more basic model. It has the cell means mu ij in it, like that. And we define some new parameters. We define mu bar I dot to be the average mean in the ith row. Now that's kind of tricky because it's an average mean. It's not the average of the data in the ith row, it's the average mean. So if we had, just to put a small little example here in front of your eye, if we had in a given row, say 3 cells, there's a mean in there, mu 1, 1. There's a mean in there, mu 1, 2. And there's a mean in there, mu 1, 3. And then the mu bar, it would be 1 dot, because I'm in the first row. Mu bar 1 dot would be the average of those 3. Okay. If you think about the actual data, this is not the average of the data in the first row. You know, I might have 5 observations in this cell, I might have 15 observations in this cell, I might have 2 observations in this cell. The average of those, or however many there would be, is not what this is. Okay. So this is the average of the averages. So watch out for that subtle little difference going on there. And then similarly, working down the columns, we have mu bar dot j. There's the formula. It's the average mean in the jth column. The average mean in the jth column. Now, you've been seeing some SAS output in numerous handouts that I've given you so far, and you'll see more as we go along. But one of the things you noticed in SAS is that when it's giving you sums of squares, it's giving you type 1, type 2, type 3, and even type 4 sums of squares come out of SAS. So what this is saying is that the type 3 sums of squares in SAS, which are more traditionally and historically called the weighted means analysis. The type 3 sums of squares in SAS test the following hypotheses. and this is the big deal. So for factor A, it's saying the average in row 1 equals the average in row 2, etc., equals the average in row A. Then for factor B, the hypothesis about B is that these column averages are all equal. And then the last one got cut off at the bottom of the page here for the interaction. Basically saying is that if you fix a row I, another row I prime, and then you fix a column J and a column J prime. So there's a cell there, 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 and there. This is saying, fixing J, take the difference on the two i's. So the first expression is this difference right there. And then the second expression here, it's got J prime in both of them. So we're over in that column, and it's got two different rows, I and I prime. So the second one is this difference here. This is this difference, and this is that difference, and the hypothesis says that those two differences are the same for all combinations of I and I prime and J prime. So all the way across the table of means, we have these equalities. These hypotheses for the unbalanced problem, a little more detail, it says a type 3 output for testing factor A. Here's the hypothesis about factor A again. It's going to use this sum of squares A, which is defined in this way. So there are three pieces in this formula. There are AIs, which are just constants, basically. B squared over the sum of the reciprocal of the sample sizes, summed on J. And the VIs are more in line with the actual data. The VIs are the average mean, sample mean now, the average sample mean in a column in row I. The sum is on J. So this is like an average of means. That's not the same thing as the average of the data in the ith row. It's not the same thing. So it's an average of those means. That's the VI. And the C is then sort of an overall average calculated this way, sort of an overall weighted average, basically. So anyway, these formulas are suitable for even hand calculation. Back in the original days, before the days of computers, this is the way people calculated sum of squares A by hand. They did this kind of arithmetic. So the point of showing you these formulas isn't that I'm worried about you using them to do calculations, is to just put them in front of your eye and say, you can see this is different from the regular sum of squares A. It's not the same thing. But this is what's produced by Sass's type 3 sum of squares. Of course, you don't see this in SAS because SAS never shows you the formulas that it's using, right? It just gives you the answers. But this is what it's calculating. Now, there's a similar statement about B, which I didn't write down here because it would be parallel to this. So this is enough to give you the idea as to what's going on here. So now turn the thought to something else here, something that you encountered last semester, I'm sure. If you consider the effects model, alpha I, beta j, alpha beta ij, we can turn to a regression view in analyzing the data. So here's some notation. R of alpha slash mu is the regression sum of squares in fitting alpha I after fitting mu. R of beta slash mu alpha is the regression sum of squares in fitting beta j after fitting first mu and alpha. Then the type 1 and the type 2 sums of squares in SAS can be described by this model. So here's the model that we would type in SAS, pretty much that way. These sources of variation have degrees of freedom, and those are the familiar degrees of freedom we've encountered before. Now, if we're dealing with type 1 sums of squares, type 1 sum of squares, the sum of squares for A is R of alpha slash mu. For B, R of beta slash mu and alpha. And then for the interaction, it's R of alpha beta slash mu alpha beta. So these are all sum of squares regressions for various kinds of models. The type 2 sums of squares, over here in this column, are a bit different. For A, R of alpha slash mu beta. For B, R of beta slash mu alpha. And for interaction, the same as before. And so we have this. And the main thing to notice here is that there's a difference here versus there. So how does SAS, how does the program know what it's calculating? Well, basically the order in which you type these factors into the model determines that. So the variable that you type in first, I've just called it A in this handout, but whatever its name is, the variable you type in first is the one that's going to be used here. And the one you type in second is going to go here. So the point is that in type 1 sums of squares, you're first of all going to be fitting the alpha parameters, and then secondly, on B, you're going to be fitting the beta parameters after you've fitted the overall mean and the alpha parameters. So now we've seen a little bit about what is type 1 sums of squares in SAS, those things. What's type 2 sums of squares in SAS, those things. What's type 3 sums of squares in SAS? Well, that's stuff we had at the top of the page, right? And we haven't talked about type 4 yet, and we won't worry about that for now. All right. Now let's go on to what I call here case 1. case one is that all Nij's are greater than 0. That is, we have no empty cells. No empty cells. In this case, we simply say, use the type 3 sums of squares in SAS. Do that testing and be satisfied with it. Okay. Now, as far as some estimation goes, here's some parameters. The mean in the IJ cell estimated by the sample mean in the IJ cell. That's pretty natural. And the standard error of that thing is, well, this is our usual formula. It would be the square root of sigma squared over Nij, and then we have to estimate the sigma squared. So that's our normal formula for a standard error of a sample mean. Then if we wanted to estimate mu bar I dot, we would use the sample analog of that, namely this. And then we have to figure out, well, what's the variance of this thing? And that's, again, a one-step consideration. We basically would say, this is the sum of independent random variables, and the variance would be 1 over b squared, squaring that constant, and then the sum of sigma squared over Nij. And that's what you see written in here, taking the square root of that. So the formula for the standard error, I'm trying to say, is an obvious thing. It's no big deal. Just think of a very, very first principle, and you'll see it. And then the parallel result for the column average, there and there. Now here's a little indication of some lines you can use in SAS. Estimates can be obtained with LS means AB. Standard errors can be obtained that way. So if you want these numbers calculated in SAS, those lines will give you some output. The comment at the top of the page here is an important one because we're often interested in talking about pairwise differences. What's the difference between the first row and the second row? So you form a difference. How do you make a statistical inference about such a difference? Well, you take the difference of the simple estimates. We've always done that. How do you find the variance of such a difference? You add the two variances together. And so we have all the pieces to handle this problem. So I didn't write out any new formulas here for you to think about. Example coming up, but before we get to the example, let's look at case 2. Some Nij's are equal to 0. We have empty cells. So, and I'm punting on this case because it's very messy to deal with. It says here, just as a loose comment, in this situation, use type 4 sums of squares in SAS, but be very cautious because it may not be appropriate. And SAS isn't going to tell you whether it's appropriate or not either. So it's something that if you encounter a problem like this, you got to do some reading, you got to do some investigation to find out some background information as to how to handle it. Okay, let's take a look at example 1 here. So this is from Millikan and Johnson's book on messy data. Here's a very small data set which has 2 levels for the row factor A, 3 levels for the column factor B. And so we have these 6 cells, but the sample sizes are 3, 2, 3, 2, 3, 3. Unbalanced sample sizes. So the first approach I took to this data was to set it up in Minitab. So this doesn't show you the actual spreadsheet of numbers, but basically you can get a hint as far as what's going on here. C1 is factor A, C2 is factor B, and C3 is the response. Whatever it is, I don't remember the context of this data. All right. So notice the Minitab commands that I've used here, actually just one line. It's very simple to use. So this is unbalanced data. I'm using GLM in Minitab, and it turns out to be basically a piece of cake. So here's the ANOVA table that's produced by Minitab. There is a column for degrees of freedom. C1 is A, 1 degree of freedom. C2 is B, 2 degrees of freedom. The interaction has the product of those 2 numbers, or 2 degrees of freedom. And that leaves 10 left for error and 15 for overall total. So it first of all gives us sequential sums of squares, whatever those are. Then it gives us adjusted sums of squares. Then it gives us adjusted mean squares. And those are the ones we're going to use in the F statistics. So you notice down here, the error mean square, adjusted mean square, is 2. So that's an easy denominator. So dividing the 61.7 by 2, I get that F statistic for A. Dividing the 38 something by 2, I get the 19 for B. And dividing the 35 something, highlights it. So we have interaction, we have factor A effect, we have factor B effect. So what I'm telling you that anyway is that in Minitab, if you use the so-called adjusted sums of squares, then these are the calculations that I want for testing of the unbalanced case. The sequential sums of squares column has got something to do, given the name, has something to do with what we talked about back on an earlier page when we were talking about that regression approach. In here, it matters which one comes first and which one comes second. It doesn't matter there, it matters here. So these would be called sequential sums of squares. Anyway, that's where Minitab is getting its language from. But as you can see, how do I analyze the data with unbalanced sample sizes in Minitab? It's very, very, very simple to do with the GLM command. Okay. Now, take the same data and throw it into SAS. So that starts at the bottom of the page here. So here's the SAS file. First of all, the data is entered, and there it begins and continues on the next page. And finally, we end up near the bottom of the page with type 1 and type 3 sums of squares. Now, what you can turn the page back and check is that these are what we got in mini tab. So mini tab is giving us the type 3 sums of squares and F then statistics from them. Okay. What else does SAS give us? Well, I had asked for some other stuff. What did I ask for? Oh, here it is, right here. On page 6. RGLM model. Least squares means on A, least squares means on B, least squares means on AB. And I'm specifying p-value for a difference, and I want standard errors. So with those calls, I get, for example, for factor A, this table here, I get the two means, I get the two standard errors, I get a p-value for a single mean, and then I get a p-value for the difference between the two means. Then when I go to factors B, which is 3 levels, I get 3 means, 3 standard errors, and those usually aren't very of interest. But here we have a table about the differences, making comparisons, and so there are 3 differences that are involved here, and here's the p-values for those tests. And I don't know if I'm going to say anything about this. This is the stuff about the interaction parameter that I called for. And, you know, it was an important set of data for me. I would want to look at this very carefully. But this is sort of an artificial data set, just illustrating unbalanced data. So I'm really not interested in trying to sort out what we're seeing here among all this stuff about the interactions. Okay, here's another set of data. Again, a very small set of data, as you see here. 2 observations, 1 observation, 3 observations, 3 observations, 2 observations, and 3 observations. So you see we have unbalanced sample size in this 2x3 layout. Minitab output. Here's the command. Notice one line is doing the job for me. GLM. Then I further asked Minitab to do a little more. I said, I want pairwise comparisons on the factor bone. That's the column factor there. I want to use Tukey pairwise comparisons. And I don't want to do any hypothesis tests. So what does it give me? Well, the first thing it gives me is the ANOVA table. And here I'm going to look at the adjusted sums of squares and mean squares, the F statistics, and their p-values. So the first one is not significant, the second one is highly significant, and the third is not significant. So that's what we see with the F tests, very simply done. Now, the program goes on and talks about the Tukey method, 95% confidence level. And here's the sort of the underlining result. Bone 1 and 2 are equal. But then bone 3 is different from those two. So I'll just put it down. So this is Minitab's attempt at the underlining method. Now it gives us a little more detail yet in what comes out. Well, it starts down here at the bottom. It says, bone equals 1 subtracted from bone equal 2 and bone equal 3. So it's going to take those two differences really. And here's the confidence limits. And the center of the interval is the estimate, of course. And we have a little graphic over here as well. And then there's one other difference, subtract bone 2 from bone 3. Here's the confidence interval here. So these confidence intervals that we have here are Tukey simultaneous confidence intervals for these three pairwise differences, right? That's what I told the program to do. Now, I didn't run this data through SAS because in the previous example we saw what was going to happen. You get basically the same results in SAS as you do in Minitab, and it's so much more convenient to do it in Minitab. So that was my leaning in that direction. Okay, so that's the end of that handout on unbalanced data. We've got a couple of SAS handouts to look at. So let's find out where they are. Pass on and yield. Yield is the response. And we have 4 groups. So this is some fiddling around with prints. And I finally come to proc GLM to do some calculations. The model is yield equals group. E squared mean group slash T-diff. E squared mean group slash T-diff just equal 2B. And then E squared mean group slash T-diff, P-diff. Then means group slash CL-diff, that's the confidence limits now, 2B, alpha equal 05. And then finally means group slash LSD. So I'm just trying to contrast, what do all these things do for us in SAS? There's too many options, I think, here, in a sense. So let's just take a look at what's produced. So first of all, we have a print of the data. Then we have the means and standard deviations for group 1, group 2, group 3, group 4. then we can go to the third page, and we see the ANOVA table. And the F statistic is high, the p-value is low, we have a significant factor effect there. The information for type 1 and type 3 sums of squares down below are identical, so nothing new happens there. But this is balanced data, of course. So then we go on and we have the least squares means procedure. So at the bottom of this page is the means. And then we get these pairwise comparisons, test statistics and p-value. Significant, 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 not significant, not significant, not significant. So we have these pairwise tests that are going on here. Now, there's a little warning here in SAS that says to us, these are not simultaneous tests. They're individual tests, so each one is run individually at, say, a 5% level. So we need to remember that in looking at this output. They're not simultaneous. So now we're going to adjust for multiple comparisons by using the 2B procedure. Here's the means. Here's the table for the pairwise comparisons using 2B's simultaneous methodology. Significant, significant, not significant, not significant, not significant, not significant. So there's a little bit of a difference in the conclusions if we use 2B's simultaneous tests, pairwise tests. But anyway, you saw the line in the code that generated this output. So if on a given day you wanted these 2B simultaneous tests, you see how it could be produced. Let's see, what's this? I think I have to go back and look. This is probably identical to turning back one page. This right here. They're produced by different code, but the output is identical. So we can skip by that. So then we have 2B standardized range HSD test on U. This is going to control simultaneously experiment-wise error rate. So here's some typical things with 2B's method. And it gives us this kind of a layout. Here's all the pairwise comparisons. Notice how they're doubled up. There's a 1 minus 4 and a 4 minus 1, for example. But we get the confidence limits, and then there's these stars over here, which are going to star the intervals that do not contain 0. So if we look at them, the ones that do not contain 0 are these 4 that are starred here. The others contain 0. Then there's an attempt in this last layout to do kind of an underlining procedure. Here's the group members, group 2, group 3, group 4, group 1. And here's the underline. So the underline tells me those three are equal. And then the gap here tells me this one is different from those two. So here's the three A's. And this one is different from those three. Okay. This is some old data again, the tree seeds. Where the variables were state of origin, block, and then the response was the growth of the tree. So this is a two-factor set of data. And so we begin with rock GLM. Here's our model. Growth is equal to state and block. Then I ask for means on state and block. I ask for means on state, confidence limits for the difference, Tukey method, alpha equal 0.05. Then least square means state slash t difference, t test for differences, adjust equals Tukey, and that's what we have there. So this is my main output right there. Let's take a look at what's produced by that code so far. So we get the ANOVA table. We have the type 1 and the type 3 sums of squares, which are identical. And we have a significant state and non-significant block. And we get some means and standard deviations coming out here. The 4 states, 6 blocks, there they are. Then we're going to get the Tukey's confidence limits. Here's all the underlying differences between the 4 states. And here's the estimate, the difference in the sample means. And then here's the 95% confidence intervals. And it's starring the ones which would not be 0. So there's a lot of them that don't be 0 there. So what's next? Least squares, means, multiple comparisons, Tukey. Here's the means for the 4 states. Here's the t-test comparing pairwise the 4 states. And it's easy to see what's significant and what isn't significant. And then we can look at so this is the new stuff that's coming out of the stats. So that kind of stuff was things that we've done before. The new thing in this particular handout starts right there. I'm going to output a brief data set called new, and I'm going to put in the residuals. So that's how it's done. And then I run it. And I print that data. The data is called new. So when I print data equals new, what you see is this stuff at the bottom here. So here's my original columns, 1 through 4, 1 through 6, the gross data, and then here's the residuals. So this is the new data set with the residuals in it. Now what am I going to do with these residuals is the question. Well, now I'm going to use proc GLM, data equals new, class is state, model resid equals state, mean state slash test equals BF. So basically what I'm doing here is to run the means test on the residuals. So the residuals were calculated from the initial GLM model and so forth. And I get those residuals, put in this new data set called new, and using these residuals, I'm going to do the means test on these residuals. So the question is basically answered here. If I have a randomized complete block design, how can I use the means test? We talked about the means test when we had one factor, right? How do you do the means test if you've got two factors? In particular, a randomized complete block design would be the first example coming to mind. Well, this shows how it would be done. So anyway, we get this new data set printed out. Then stuff. I'm not too interested in that really, because this is about the residuals, right? And what I'm finding is that nothing interesting is going on here. For example, the F value is 0. Absolutely no differences going on. The F value is again 0 or 0. Absolutely no differences going on. So this is not of interest, but it just sort of comes out from SAS. It doesn't know any better, and so we just have to skip by it. But then at the bottom of the page here it says Brown and Forsyth test of homogeneity of variance, and so here's our the means test based on the residuals, and basically with this high p-value or low f value, say either way, we would accept H naught of equal variances. Okay. So conclusion is kind of quick once we know what we're doing there with that test. And the final page is just some descriptive stats again. Okay, so the point of this SAS handout was basically to illustrate how can we test for equality of variance in a randomized complete block design. Basically, the trick is to convert to residuals. And you do that. Now, if you were doing hand calculations, residuals are hard to do with hand calculations because you start getting into messy decimals and so forth. But if you've got software that gives you the residuals, you can put the pieces together to do the means test on the residuals sort of by hand. But SAS does it automatically for us. The problem with SAS is, again, remember that SAS doesn't drop the zeros, right? So if you wanted to do that, you've got to switch over and do some hand work. I'm out of things to say today. Looking at the clock, I timed it just perfectly again to end at the right spot. How do I do that every time? Stuff is just